Welcome to part 4 of sequences and series. This part is going to focus on sigma notation, which is an extension of our understanding of sum of. So sum of, that is when we are adding all of our terms together to get a particular numerical value. Now the symbol used for sigma, it has this structure. Okay, so this, we need to familiarize ourselves. When we see this, we're going to be often performing summation type calculations. An example of this can look as follows. The way we can read this is the sum of the terms running from a substitution value k is equal to 1 until the substitution value k is equal to 8 plugged into this function, establishing what is the sum of those terms. Okay, so we know this part here is the sum, so that's a plus. This number here at the bottom is our starting value point for substitution. So this is our initial substitution value, right? K equals 1. Can you see the K here? So it means you're going to sub it in. That's the first value. And then 8 represents the final sub value. So once you've substituted value 8 in, you needn't continue to go to 9, 10, etc. So let's try and figure out, we're needing to add a whole bunch of terms together using inputs to find an answer. Now, the question you might wonder is, how many terms are there over here? Right? Because we actually can't see the series here. So a rule of thumb is to establish how many terms there are. You are going to say the number of terms is equal to the value at the top of sigma less the value at the bottom of sigma plus 1. Okay, so we usually denote it with T. Any letter can work, but you take the number at the top, you subtract the number at the bottom, and then you add 1. So in this case, if we look at how many terms would be in this series, you would take the top number 8 less bottom, which is 1, and to that you add 1. So that means we've got 8 terms over here. 8 less 1, 7 plus 1. So that means we've got a total of 8 terms over here. So we've got 1, 2, 3, 4, 5, 6, 7, 8. And we need to find the summation of all of those 8 terms. Let's establish what the first one is. If we plug in k is equal to 1, right? So 2 by 1 less 1. 2 times 1 less 1. That's 2 minus 1 is equal to 1. So that's your first term. Let's do it as well for the second term. So that's 2, and our next substitution value is 2 less 1. 4 less 1, 3. Okay, so we needn't do it for all of them. Let's perhaps do it for the last one. 2 by 8 less 1. That's 16 less 1. That's 15. So our final term that we're adding there is 15. Okay, I'm just going to do one more for safety's sake, just so that we can establish whether this is arithmetic or geometric. 2 by 3 less 1. That's 6 less 1 is 5. Okay, that's more than enough information. Now, looking at the series we have so far, can you guys see that this is an arithmetic series? Because of the constant difference plus 2 every time. Plus 2, that's an arithmetic series. So sigma sum, we are going to perform the SN notation, the sum notation of an arithmetic. Okay, I'm just going to take it up here. So SN is equal to n over 2 multiplied by 2a plus d n minus 1. Okay, and now we can fill in all of our values. So we're basically calculating the sum to 8, because remember we've established now that there are 8 terms over here. That's what the relevance of using this formula was. So the sum to 8 terms, we've got 8 over 2, 2 by a is our first value 1, plus difference is 2, multiplied by n is 8, less 1. Okay, and then we can just get the answer to that expression. That is 64. So the answer to this expression here, this sigma expression, is equal to 64. When you add all of the terms together, the series terms together, it's going to yield you basically an answer of 64. You needn't figure out all the terms. That's not what they're testing. It's using the understanding of start point, end point into a given function to gather some information about your series, establishing arithmetic or geometric, noting that this is a sigma summation, and then performing your SN. Right? 3 plus 6 plus 12 plus 24 plus 48 plus 96 plus 192 in sigma notation. Okay, so they want you to do it involving the symbols and the general rule. So this is all you're given. So we need to establish, is this an arithmetic series or is it a geometric series? To go from 3 to 6, well, I can see a multiplication factor by 2 because that's going to run consistent throughout. Okay, so there's no difference that's continuous, but more a ratio. So this is a geometric series. Okay, so starting off, we write our little sigma notation. There we go. Our input value, we're always going to start at 1. So we can assume this starts at 1. So you can call this P or K or any letter as long as you maintain consistency throughout. So I'm going to call it K. So K is my substitution value 1. And then until what value am I going? Can you see that there is 1, 2, 3, 4, 5, 6, 7 terms? So we said top minus bottom plus 1 is the number of terms. So if we have a total of 7 terms, we can now try and figure out what is the final value of substitution. So the top number we want to figure out. The bottom number is 1 and we plus 1 to that. So clearly, cancel, cancel. The top number is equal to 7. So that goes here. And now all that's missing here is the rule. So taking our understanding of a geometric, Tn is equal to a times r to the power of n minus 1, where a is our first, r is our ratio, n minus 1. Now that Tn, this is the general rule. That is what we're going to apply our inputs to. So this part here is what goes next door. And this is finished. That's how you write it in sigma notation. Start at your substitution 1. Figure out how many terms are involved. You can count 7, so 1, 2, 3, 4, 5, 6, 7. But just to verify it, you can do that. And then it's establishing the general rule based on the type of series you have. Expand this sigma notation. The sum of all the terms with the general rule 2 plus 2k with our starting input value 3 up until input value 8. We basically need to write out what the series is. So I like to just do my inputs here on the side. When k is equal to 3, remember, this is your initial. So this is what you're going to plug in. So it's going to be 2 plus 2, and we multiply it by that k value. So we're using BODMAS, 2 by 3 is 6, plus 2 is 8. That's the first term. Next up, you're going to do your second one, which will be the iteration after 3. So that's 4. So 2 plus 2 by 4. 2 by 4 is 8, plus 2 is 10. So we're starting to see this. I'm going to write out the structure. So the first one is 8. The next one is 10, separated by plus because sigma is addition. Just for more information, how many terms are there? It's top less bottom plus 1. Now the reason I use this example is so we can see when our k or p value is not 1. So our top value is 8. The bottom value is 3 plus 1. 8 less 3 is 5, plus 1 is 6. So that means we've got 6 terms that we need here. So 1, 2, 3, 4, 5, 6. Okay, I'm just going to do the next iteration because then you can kind of get an idea of what would follow. So the next iteration is k is equal to 5. That's 2 plus 2 by 5. That's 10 plus 2 is 12. Okay, so clearly here you can see that this is an arithmetic series. Also, because of the fact that there was no exponent here, it is usually going to be arithmetic then. When there's an exponent involved, it's usually geometric. And we can continue this one here. 8 plus 10 plus 12. We're adding 2 each time, so that's 14, 16, and 18. Okay, so that's great stuff. Determine the number of terms in the series. So number of terms, that means you're required to find the n value. And they're telling you here it is. We have sigma notation. P starting at 1 is our input, running up until n. For this expression here, 3 raised to the p, and the series is equal to 1092. So we have the summation. We have what it adds up to. We need to figure out how many terms, when we plug it in here, is going to yield the summation of this. Okay, so I like to always establish the pattern itself. So if we input our starting value p is 1, 3 raised to the power of 1 is 3. 3 raised to the next consecutive value is 2. That's 9. And then let's do one more. 3 raised to the 3, that's equal to 27. So if our series is 3 plus 9 plus 27 plus, and we continue, when we add all of that, it's going to equal to 1092. That's the situation we have now. We just want to establish how many terms we have that added up to it. Clearly, we can see a times by 3 factor. Okay, you guys can see that? What does that mean about this type of series? It's a geometric series because of the constant ratio. So using series is summation. We're going to perform SN on geometric series. That is A times R raised to the power of n less 1 divided by R minus 1. And we're going to plug in everything. We know the value of the summation. It's here, what it added up to. So the 1092 is the answer that replaces Sn. The first term upon doing our substitution is 3. The ratio value is also 3 raised to n less 1. And now we can see our task is to make n the subject of the formula. So doing some bod maths, this is in the denominator, 3 less 1 is 2. So this division by 2, I'm going to multiply it onto the other side. So that means on my left-hand side, I have 2,184, and I'm left with 3 times 3 to the n less 1. Here, I have a multiplication factor of 3, which is timesing. So I'm going to divide on both sides to get rid of that factor. That is 728 is equal to 3 raised to the n minus 1. We get rid of the plus 1, the constant, so we add it on to the other side. 729 is equal to 3 to the power of n. Now we want to try and write it in the same base structure. If you don't know this at the top of your head, I'll show you how to do it on the calculator. We want to try and get these to both be the same bases, right? Base 3. So you take the number that's not a prime base, which is 729. You press the equals button, shift, and then you press this one that says fact. There we go. So that is 3 to the power of 6 is equal to 3 to the power of n. Now, because the bases of this are the same, we can see that implies that the exponent value also has to be the same. So that means n is equal to 6. So to answer the question, determine the number of terms. Therefore, it is 6 terms. That concludes part 4 of our sequences and series chapter. Thanks so much for sticking around to the end. A like and subscribe would really help us grow our channel. And please do share this with one of your grade 12 friends so we can all get ahead together in maths.